Hey Algebra 1, in this third and final video on compound inequalities, we're going to look at two examples of special cases in compound inequalities and why they are special cases. So if I have this and inequality, once again, a verbal and inequality, I have negative 12 less than negative 3x and 2x is greater than 20. Okay, so it's an and inequality, it's verbal, so I'm going to go ahead and solve it like it is a normal and inequality, which means I first need to switch the 3x and the 12 around because I want my variable on the left side. So negative 3x is greater than negative 12, because when I switch what's on the left side with what's on the right side, I need to make sure that I switch the inequality around as well. So now I just go ahead and solve it. So negative 3x gets divided by negative 3. I got to do that on the same side here. So when I do that, my x's cancel, I'm left with x here, I'm left with positive 4 here. My sign also has to switch because I divided by a negative. So all my numbers less than 4, and when I go to divide by 2 in the second inequality, so 2x gets divided by 2, 20 gets divided by 2, I get x is greater than 10. Okay, so this inequality tells me I need to look for numbers that are both less than 4 and greater than 10. Problem is though, if I go to graph this, okay, because I know how to graph all my numbers less than 4 and greater than 10. So let's see here. So remember, the idea of an and inequality is that we're looking for overlapping regions. Okay, so if I'm looking at less than 4 this way and greater than 10 this way, there are no numbers that overlap here. So when that happens, we consider this a no solution inequality. The reason being is that there are no numbers that satisfy both of these conditions. There are no numbers that exist that are less than 4 and greater than 10 at the same time. If we look at an OR inequality, so let's say we have the compound inequality negative 2x plus 2 is greater than negative 8, or x plus 1 is greater than 4. If we solve both of these inequalities, let's see what happens. So with this one, I'm going to go ahead and subtract 2 from both sides of the first inequality. When I do that, negative 2x plus 2 minus 2 causes me to cancel out my 2's, left with negative 2x here, greater than negative 8 minus 2 is negative 10. And then I go ahead and divide by negative 2 on both sides to get rid of that coefficient. I'm left with x is now less than positive 5. So I'm looking for all numbers that are less than positive 5, or when I go to solve the second equation by subtracting, or I'm sorry, the second inequality by subtracting 1, x plus 1 minus 1, 1's cancel, left with x, didn't divide by a negative number, so my sign stays the same, and then 4 minus 1 is 3. So I'm looking for all my numbers that are both less than 5 and greater, or greater than 3. Okay, so that's the big operator there, is that we include both of them here. So let me give myself some room. I'm going to draw my line here. Alright, so remember, OR means we include both numbers here. So put 3 over here and then 5 here. When I go to graph this, remember, we include everything. So open circle over 3, and I go everything to the right. And then open circle over 5 and everything to the left. Notice how both of these regions overlap. And I'm basically covering everything in between, even though we're used to in an OR inequality for there being a gap there. That means when we do this, when we take an OR inequality and have regions overlapping, this is a infinitely many solutions compound inequality. It doesn't matter what x is, because it's either going to satisfy one or the other, or both, in which case this covers all real numbers. Okay, so more specific definition for my solution would be all real numbers. Okay, so I hope this answers any questions you have on solving inequalities. Your homework can be found on Delta Math and on our Google Classroom with homework number 17. If you have questions, make sure you message me. We'll talk to you soon, guys.